Hi folks, welcome to chapter 2. This is the chemical level of organization. So this is the chapter where I remind you that chemistry is important and do some basic chemistry with you. It's not hard chemistry. It's not a chemistry course, but it's some basic chemistry as it applies to biological systems or humans in this case. This is the hierarchy of life. I'm going to remind you the hierarchy of life runs from the basic unit of matter, which is atoms, up to the organism. Now this chapter is going to cover the atoms, the molecules, and the macromolecules. And in addition to that, we'll do some energy concepts. And this is not difficult thermodynamics by any means, but we will talk about a few energy concepts in today's lecture, in this chapter, one of the mini lectures today. Okay, so let's start talking about atoms, how they combine to make molecules, and how the molecules combine to make macromolecules. Which elements or a type of atom are the most common in the human body? I always think to myself, schnapps. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, schnapps. And if you look at here's carbon, hydrogen, nitrogen, oxygen, phosphorus. Sulfur's way over here at 0.04%. Now, why would I stick sulfur in schnapps if it's sodium's more common, chlorine's more common, magnesium's more common? Well, because sulfur is found in two of these amino acids that we're going to talk about. It's found in methionine and cysteine. And in fact, when you burn your hair, the reason why you get a sulfur smell is because you're burning methionine and cysteine. So I do put sulfur in there. Besides that, I couldn't make this joke right here, schnapps, peach schnapps or whatever schnapps, if I didn't put the sulfur in there. Now realize that schnapps is not perfect. You have 1.8% of your body is calcium. And by the way, this is by weight, not by molar, not by numbers of atoms, but by weight. We also have sodium and potassium in there, and chlorine. And it's actually chloride. It exists as chloride. It's not ground state chlorine, but we'll get into some of that. So you can see there's some other things in there in addition to schnapps. When atoms or elements appear in very, very small amounts, less than 1/10,000th of a percent or 2/10,000ths of a percent, when they appear that infrequently, we call them trace elements. Sometimes we call them micronutrients, and it's not because they're small. It's because they appear in very small amounts versus macronutrients where they appear in higher quantities. So, but we call them trace elements in this text in our lecture. We'll call them trace elements versus micronutrients and macronutrients. All right, so think schnapps, the most common elements in the human body. This is a video of the atomic structure. It's going to do the Bohr atom, and what that means is you're going to say, what's the Bohr atom? Bohr as in Niels Bohr. So the Bohr atom, and what that does is it puts the neutrons and protons in the center in the nucleus, which they are, but then it allows the electrons to orbit around the nucleus, and they don't actually do that. I mean, it's a great way to think about it, really, for now and in our level. It's probably not a good way to think about it if you ever take analytical chemistry or physical chemistry. In fact, it's not a great way to think about it. But for biologists, we can think of these atoms as the Bohr atom, which is the nucleus containing protons and neutrons, and the electrons orbiting around the nucleus. So let's take a look.
An atom is the smallest particle of an element that retains the properties of that element. Atoms are composed of smaller particles called protons, neutrons, and electrons. The central nucleus contains protons and neutrons, while electrons move constantly around the nucleus in concentric regions called electron shells or energy levels. A proton has a single positive electrical charge, and an electron has an opposite negative charge. Neutrons are neutral with no electrical charge. Each element is uniquely defined by the number of protons in an atom of that element. For example, only carbon atoms have 6 protons, and only potassium atoms have 19 protons. The atomic number is the number of protons in an atom of a particular element. The number of protons equals the number of electrons, making atoms electrically neutral. Electrons are so small that they have almost no weight. The atomic mass is the sum of an atom's protons and neutrons. The number of neutrons in a particular atom, and thus atomic mass, can vary. Atoms that have the same atomic number but different atomic weights are called isotopes. Electrons occupy electron shells in fixed numbers. The first shell, closest to the nucleus, holds a maximum of 2 electrons. The second shell holds 8 electrons, and the third shell can hold up to 18 electrons. Subsequent shells can hold higher numbers. The outermost shell, known as the valence shell, holds a maximum of 8 electrons. The electrons in the valence shell determine an atom's chemical bonding properties. Atoms such as helium, whose outermost electron shells are filled, have stable structures and are chemically inactive. Atoms with partially filled valence shells tend to lose, gain, or share electrons to either empty or fill their outer shells, producing a stable number of valence electrons. The number and kind of bonds an atom will form depend on the number of electrons needed to fill the valence shell.
Okay, let me tell you some key. You should play this. You should rewind this video and play that again. It's chock full of concepts that I'm going to test you on and make you connect some dots. So let me just recap some very important things going on here. Probably first, the most important thing going on here is you have to know the nucleus is composed of protons and neutrons, and the protons are positively charged, and neutrons are neutral. And the electrons are have very little mass compared to protons and neutrons, and therefore biologists don't even count the mass of the electron. It's something like 1/2000th the mass of a proton. So we don't even count it. Now, analytical chemists do, physical chemists do. Biologists don't count the mass of electrons. So first of all, know what the atom looks like. Big concept. Secondly, and they said this right here, what makes an element that element is the number of protons. So for example, if an element has 6 protons, it is carbon. And if it doesn't have 6 protons, then it's not carbon. The number of protons is what makes it that element. The number of neutrons can vary, but as long as it has 6 protons, it's carbon. If it has 7 protons, it's nitrogen. If it has 8 protons, it's oxygen. If it has 19 protons, it's potassium. So the protons, or the atomic number, is what makes that atom unique and makes it that particular element. If the number of protons change, which only happens in radioactive decay, then, which we won't talk about, well, we talk about a little bit, but not in detail. If the number of protons changes, then the element changes. However, you can take a given element, like carbon, and you can vary the number of neutrons, and it's still carbon, but it's a carbon isotope. Another big concept here is when you look at a periodic table, those elements are all at the ground state, which means the number of electrons equal the number of protons. So at the ground state, meaning no overall charge, carbon has 6 electrons. There's no overall charge on it. If it has 6 positively charged protons, it must have 6 negatively charged electrons to be at the ground state or neutral. Now that's not to say that some elements don't gain or lose electrons. They do. But at the ground state, the number of electrons equals the number of protons. All right, so that's a big concept right there. The other big concept is atomic mass. Atomic mass is simply the number of protons plus the number of neutrons. Now you might scratch your head and say, how come it's not the number of protons plus the number of neutrons plus the number of electrons? Well, because you would actually need 2,000 electrons to equal the mass of 1 proton. And no element has 2,000 electrons. So we really discard or ignore, really. We don't discard. We ignore the mass of electrons because they're so light. So the atomic mass is simply the number of protons plus the number of neutrons. And by the way, protons and neutrons, although they don't have identical masses, they're very, very close. So that's another big concept there. This concept right here is showing you energy levels or shells. Electrons exist in these shells. You have the first shell, the second shell, the third shell, etc. And even within the shells, we have, which I'll talk about just briefly, we have subshells or orbitals. We call them orbitals, and they have particular shapes, by the way, and it's pretty cool. We'll talk about that a little bit. And before I go on, the outermost shell containing these electrons is the valence shell. Now I hesitated a little bit. These I'm going to talk. I'll explain something in a second, but these don't fill perfectly. That means, let me just give you an example. The fourth energy level or fourth shell will actually have some electrons in it before you finish filling what we call the third energy level d orbitals. So 4s will fill before 3d. And so, as always in science, it's not as clean as we make it sound when we first start teaching it to you. Everything's on a continuum. It's not as matter of fact as we'd like it to be, or as we make it. Actually, I don't like it to be matter of fact. Interesting science is the exceptions to the rules. But we always teach you the rules. So it's not as simple as the rules we teach you. But for the most part, these electrons fill these shells: first shell, second shell, third shell, fourth shell, and so on. And then this shows you some bonding, which we'll come back to. It's actually showing you a nonpolar covalent bond, but I don't expect you to know that yet, so we'll come back to that. All right, so that's the atomic structure. A little song for you that you should memorize. I'm kidding, you shouldn't memorize it. A little song for you about the periodic table and the elements.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
And in case you're wondering, that was a parody on the song I Am the Very Model of a Modern Major General from the Pirates of Penzance, I do believe, if my memory doesn't fail. So, pretty cool song. I like playing that. Now, here's the periodic table of the elements. We'll talk about its periodicity. The periodicity meaning why do we make it like this? What makes sense about it? And how does it change? How do these elements change incrementally, or what's the periodicity? We'll talk about that a little bit. So these are the different types of atoms that you'll see. And remember, schnapps. So please remember schnapps. C, H, N, O, P, S, schnapps. And sure enough, you also know that we have some electrolytes in our body, sodium, potassium, and chloride. And then, of course, we have some trace elements. We'll talk a little bit about selenium, actually, believe it or not. There's an amino acid that has selenium in it. It's called selenyl-cysteine. We'll talk a little bit about that. Vitamin B12 has cobalt in it. I'm not going to remember everything as I'm looking at this, but just giving you a smattering of this. Magnesium was on that list. and calcium was in our bone. Magnesium and calcium in our bones. So you'll talk about that a little bit. All right, periodic table of the elements. We will talk about its periodicity. Before I go on, let me just show you something. This number right here is its atomic number. That's how many protons it has. So you can see, let me erase these red dots. You can see that the atomic number, or how many protons it has, is what makes it unique. Carbon always has 6 protons. Nitrogen always has 7 protons. Oxygen always has 8 protons. Well, if carbon has 6 protons, well, how many neutrons does it have? Well, the most common carbon has 6 neutrons. How do I know? Because the atomic mass is 12.011. And you might say to yourself, well, why is it 12.011? Why isn't it 12? 6 plus 6 is 12. Because isotopes of carbon exist, carbon 13 and carbon 14. And this 12.011 is the average atomic mass of all of the carbon isotopes, carbon 12, carbon 13, and carbon 14. Now, carbon 12 is the most common carbon, but carbon 13 and 14 do exist, so the average atomic mass is 12.001. You can see that nitrogen has 7 protons and 7 neutrons. Why is it not exactly 14? Same reason. You can see that. Okay. So atomic mass and atomic number. Still is periodic table of the elements. These are called periods right here. Actually, I think I can go back and show you the periods. Yes, these are the periods right here. These are the energy levels that are filled. So the first energy level is filled. The second energy level is filled. The third energy level is filled right there. All right. So when you start talking about this, when you start talking about the periods and what's filled, you can say, well, here's the second energy level is filled. What does that mean? Well, it means you filled the first energy level, and 1s2 has 2 electrons. And then you fill the second energy level, and you have 2s2, which has 2 electrons, and 2p. And 2p can have up to 6 electrons. So if I fill the second energy level, the most amount of electrons I can have are 10. 6 plus 2 plus 2. 6, 7, 8, 9, 10. Look at, in the second period, 10 is the most electrons I can have. Neon has 10 electrons. Now, what does it mean when fluorine has 9 electrons? Well, it means that I'm 1s2, 2s2, and 2p5. I mean, see, whoops, didn't mean to erase the p, but I don't have my p orbitals of my second energy level aren't completely filled. So that's what that means. And so these periods are the energy levels that are filled. That's what they are. All right. Good. Periodic table again. I don't know what I'm supposed to be showing you here. All right, the atomic mass, atomic number, and the isotopes. We've already talked about this in great detail already. The atomic number is the number of protons. The atomic mass is the number of protons plus the number of neutrons. The number of neutrons can change, and it happens to be called an isotope. And this is showing you what, tritium? Yes, it is. To look down and look what it's showing you. So this is tritium. See, hydrogen usually is just a proton. That's what hydrogen usually is, just a proton. The ground state hydrogen, by the way, let me take that back. Hydrogen is usually a proton plus an electron because at ground state it doesn't have a charge. But what would it be if it lost that electron? And the answer is it would be H+, which is simply just a proton, which, by the way, is an acid. That's why sometimes you'll hear me say when I'm talking about acidic solutions, there's a lot of protons in there, because the definition of an acid is H+, which is a proton. So I just wanted to show you that while it's here. But there's isotopes of hydrogen. There's deuterium. This is a radioactive isotope. And tritium. This is a radioactive isotope. These are unstable. These are isotopes of hydrogen. All right. Well, what do we care about isotopes for? Well, not all isotopes are radioactive, but many are. And we use these radioactive isotopes in science. We use them to see things, see soft tissue. Because if you add a radioactive isotope to something and then you look at it with uh, X-ray paper, or in this case it's a scintillation counter you're looking at, the scintillation counter counts how many radioactive particles are hitting it. It could be alpha or beta particles. We're probably not using gamma particles, but we can look at the radioactivity, and we can see tissue by injecting or having a person eat radioactive elements. In addition, we can also use radioactive elements to ablate a tissue. Now you're going to say, why would you want to ablate? Means destroy. To ablate a tissue. Why would you ever want to ablate? Why would you ever want to ablate a tissue? Don't you want that tissue? Well, for example, if you have an overactive thyroid gland, you have hyperthyroidism. That's incompatible with life, meaning you can't live with it. Briefly, you can. You can't. You have to get it treated, or you will die. Well, the treatment for hyperthyroidism, one of the treatments, is thyroid ablation. Well, doesn't that make you hypothyroidism? Sure does. But the thing is, you can live with hypothyroidism. I'm not saying it doesn't have side effects. It certainly does. Your metabolism slows down. You gain weight. You are sensitive to cold. So it does have side effects. But you can at least live being hypothyroid, and then you can take an artificial thyroxine called Synthroid, but you can't live being hyperthyroid. So your treatment is to put you in the condition with which you can live with versus the condition that kills you. So that would be thyroid ablation. All right, these are, please don't memorize this table up here. I wanted to show you something. I wanted to show you that, what is that, 5 10,000ths? Yeah. Or, no, 1 2,000ths. It's, the mass of an electron is very, very small. All right, just tremendously small. You can see that right here. Whereas the mass, this is an atomic mass unit. So let's look at grams. Should I tell you what atomic mass unit is? Well, the atomic mass unit is the mass, 1/12 the mass of carbon-12. And I know that sounds funny, but that's an atomic mass unit. It's 1/12 the mass of carbon-12. It's also called a Dalton, by the way. So you could call this a Dalton. But if you look at grams, you can see that protons are 10 to the negative 24 grams, whereas electrons are 10 to the negative 28 grams. So you can see that there. You can see that it's very small. You can see that protons and neutrons are almost identical. They're just slightly different. All right, let's talk about some measurements here. Molarity. We talk about molarity in anatomy and physiology all the time. It's moles per liter. That's what it is. Well, what the heck is a mole? A mole is 6.02 times 10 to the 23rd atoms or molecules. That's a mole. Atoms or molecules. I mean, you can have a mole of molecules. You can have a mole of atoms. So saying mole is like saying a dozen. You're going to say, what do you mean it's like saying a dozen? It's 6.02 times 10 to the 23rd. That's not 12. I agree. It's not 12. But when you say a dozen, you mean 12. When you say a mole, you mean 6.02 times 10 to the 23rd. That's what you mean. So the word mole really is like saying a dozen. And it means a set amount of atoms or molecules. So molarity is the number of is 1 mole per liter. 1 molar is 1 mole per liter. 2 molars is 2 moles per liter. 3 molar is 3 moles per liter. Molality is moles per kilogram. I actually don't use that much in biology, do I? Oh yeah, osmolality. Yeah, I guess we do use it in biology a little bit. So moles per kilogram is molality. Equivalence. Equivalence is a mole. How do I want to say this? It's a mole of charges per liter. So for example, if you have a 1 molar sodium solution, well, sodium has 1 charge. So that's also 1 equivalence of sodium. All right? But if I have 1 equivalence of calcium, calcium has 2 positive charges. That's actually half a mole of calcium. But it's 1 equivalence because there's 2 charges per calcium. So I guess that's the best way to explain equivalence. Here's what I would like you to remember. If I say equivalence per liter and the charge is 1, because for the most part you'll be talking about sodium, potassium, and chloride, and they all have a charge of 1. Sodium is plus, potassium is plus, chloride is minus, but it doesn't matter if the charge is plus or minus, there's just 1 charge. Equivalence in molarity is the same when the charge is 1. 1 plus or 1 minus. Equivalence equals molarity. A milli equivalence is the same as a millimolar if the charge is 1. It's when the charge isn't 1 that you have to start doing a little bit of algebra, a little bit of quantitative skills. It's not even algebra. And then we use the metric system to describe different smaller quantities of molarity or larger quantities of molarity. So we say milli, micro, nano, pico. So this is milli. This is micro, like micromolars. This is nano, and this is pico. Now these are prefixes that mean 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, 10 to the negative 12. What do I mean? 1 millionth, 1 billionth, 1 trillionth. And this is really review for you. You did this in your prerequisite. I'm just going to use these words as if you know them. Please come see me if the metric system is something you're still struggling with. We can talk about it. You know, it's something I need you to know. So come see me if the metric system is not something you understand. And we'll talk about it some more. All right, the periodicity of the periodic table. This is showing you sizes. So as you go down the periodic table, you get bigger. As you go across the periodic table, you get smaller. All right. So make sure that you stay within a period when you're doing that. Like when you say as I go across from left to right, I get smaller. Yeah, but stay within a period as you do that. All right. So if you're going to sit here and you're going to say I'm going to compare lithium to strontium, well, don't compare lithium to strontium. Did you go from left to right? Yeah, but you also went down. And see, as you go down, you get bigger. So you have to, change one variable at a time as you're looking at this periodicity. As you go down a group, you get bigger. As you go across the periods, you get smaller, and that's the periodicity in sizes. Now that's at the ground state. I must tell you that when you ionize one of these elements, the size changes. So let me say that again. When you ionize these elements, the size changes. So this is ground state elements. Electronegativity is a huge concept. Let me go back. Electronegativity means I'm going to use a pathetic fallacy, and that means I'm going to use words that aren't really attributes of these elements. But here's the pathetic fallacy. Electronegativity is a measurement of how much the element likes electrons. Now, obviously, an element doesn't like electrons. The word likes is a pathetic fallacy. I mean, it's not like fluorine wants to hold hands with electrons, all right? It's not like it wants to buy it dinner. And I really can't use the word electron affinity because that's really a different measurement. But electronegativity is how much this element grabs and hangs on to electrons, how much it likes them. Okay, that's electronegativity. As you go across and up, you become more electronegativity. So as you go across more electronegativity, I'm sorry about that. As you go across the period, you become more electronegative. As you go up a group, you become more electronegative. Now, what does that mean? It means fluorine is the most electronegative element on the periodic table. How come I don't count these? Because these are inert. This whole group are the inert gases. They don't react at all because their valence shell is filled. They have a filled valence shell. The valence shell is completely filled with electrons. They can't gain or lose any more electrons. Well, they could lose, but they're more stable being filled. So they're very inert and they don't react. Here's a table of the electronegativity, and you can see fluorine. There's a reason why I'm saying fluorine. I don't really want to go into it right now. Well, I will tell you. My wife is British, and I'm starting to talk like her. They say chlorine and fluorine and aluminium, whereas I say fluorine and chlorine and aluminum. She's rubbing off on me, sorry. So fluorine, yeah, she says aluminium, by the way, and my stepson and their families over in England say aluminium. Here's aluminium. Here's aluminum for you, aluminium. So anyway, the fluorine is the most electronegative element on the periodic table. And oh, by the way, Linus Pauling is the one that assigned these numbers. He's a Nobel Prize winner. He's the vitamin C guy. I mean, he did a lot more than vitamin C, but he's the vitamin C guy. You know, he was also involved, and Watson and Crick built on his work to figure out the DNA double helix. Linus Pauling actually thought it was a triple helix, but you know, building on his work helped Watson and Crick, and he's done a lot of things. Well, Linus Pauling, brilliant. Well, used to be a brilliant man. So there you go. He came up with this scale, and it's an arbitrary scale with fluorine being 4. Now, why am I telling you about these electronegativities? Because when two atoms combine with chemical bonds, how they share or don't share those electrons has everything to do with their electronegativity difference. So we'll come back to electronegativities. How these elements ionize. Now look at this. As you go down a group, the ionization energy gets smaller. And be careful when you're looking at this graph. You have when you look at this graph, only look at helium, neon, argon, krypton, xenon, radon. Only look at that, and then look right here. Helium, neon, argon, krypton, xenon, and radon right here. As you go down a group, the ionization energy gets smaller. So it would be easier to ionize radon than it would helium. Helium would not ionize well at all. It would take so much energy to ionize it. And in fact, this whole group is called the inert gases because they don't react well. So as you go down a group, the ionization energy gets smaller. Look at this. Sodium and potassium are more stable. They're more stable being ionized. Matter of fact, they're very reactive being ground state. And if you look at sodium, potassium, look at the whole group. Hydrogen, lithium, sodium, potassium right here. Hydrogen, lithium, sodium, potassium, rubidium, cesium. You look at that. As you go down that group, ionization energy gets smaller. But even saying that, the ionization energy of lithium, sodium, potassium is not great. It's not huge. So you can see that. All right. Well, what's this showing you? As you go across a period, ionization energy gets larger. Sodium, magnesium, see right here, sodium, magnesium, aluminum, silicon. Well, you're going to say, wait a minute, aluminum dropped down. Yep, you're right. This is not perfect, but silicon has higher than sulfur, than phosphorus, than chloride. Silicon, phosphorus, sulfur, chloride. In general, as you go across the period, ionization energy increases. In general. Are there exceptions? Yeah, look at the exception. You went from here to there. There's some exceptions. But in general, you see this going up. You see this going up. You see this going up. So this is part of the periodicity of the periodic table. All right, now, valence electrons. It's a little bit tricky. It's basically the outer shell. So you have a 1 shell, and then you have the second shell. As it turns out, in the first shell, you only have 1 orbital, and it's called 1s. In the second shell, though, you can have 2s and 2p. And then in the third shell, you have 3s, 3p, and 3d. And in the fourth shell, you have 4s, 4p, 4d, and 4f. Now, you're going to say, so if I have enough electrons to be in the fourth shell, those are my valence electrons. Well, yes, I will say that. The outermost shell is your valence electrons. However, I want to tell you something. They don't always fill perfectly. I'm going to show you something. How electrons fill these orbitals in these shells is like this. 1s always fills first. Then 2s always fills second. And then 2p fills third, and then 3s fills fourth. Perfect. I have filled the entire second energy level before I ever put an electron in the third energy level. That's true. So far, so good. After 3s, I fill 3p. But I don't start putting electrons in 3d until I've put electrons in 4s. So after 3p comes 4s. And then I go back and put electrons in 3d and then 4p. So when you start talking about some elements, the valence electrons are always going to be the outermost energy level. So that's why this is saying valence electrons are 4s and 4p. But they didn't fill sequentially like that. They filled like this: 1s, then 2s, then 2p and 3s, then 3p and 4s, and then back to the third energy level. So you can see that there. And by the way, this is called the off-bow process. Off-bow process. How electrons are filling their orbitals and energy levels. That's what it's called. All right, so that's valence electrons. When you go up an energy level, the electron does have more potential energy and is less stable. So if you add energy to this electron, it can bounce up to a higher level. By the way, when an electron falls back down to its lower energy level, if you excite it, it's called an excited electron now if you bounce it up to a higher energy level. Usually it gives off light. By the way, that's the whole basis of fluorescence and phosphorescence. So it gives off light when the electron, I should say this, it always gives off energy, but it usually gives off, well, I don't even know if I'm using that word correctly. I don't know if I should use the word usually. At times it gives off visible light. So when an electron falls back down to a lower energy level, it gives off visible light. And because of that, you have things that fluoresce and things that phosphoresce. Now, phosphorescence is a really cool concept, but it has to do with spin states and stuff like that, which I'm not going to teach you. All right. Here's the off-bow process right here. This is off-bow that we just did together. All right, that's about the extent of the chemistry I'm going to do to you as far as the valence electrons and filling orbitals. All right, I'll see you in the next mini lecture.